Hello there, we're going to do one relatively short video this week. Again, if you're viewing this early, do not forget to take your quiz, and otherwise, hope it went well for you. And we'll see you in class on Monday. So today's video is going to kind of dovetail off of what we're doing in class with regard to mid-latitude cyclones. We're obviously getting into more of the sensible weather, the things that we experience. And so this is kind of off on the side, but a little bit of a lecture here on forecasting in the sense of what has gone into forecasts historically, how have we gotten to where we are today, show a couple of maps, and well, that's about it. So when we talk about weather forecasting, there's a number of things that go into our creation of forecasts, our verification of what is going on in the weather, and so a lot of what we deal with is high-end modeling systems. Being able to communicate the data, obviously massive storage needs, the processing needs to be able to run through what's effectively a series of what we refer to as governing equations. Math is what's going on to dictate the motions that occur in our atmosphere. And then to be able to actually display, again, now we just are in an era where there's massive amounts of information out there, and that oftentimes actually presents some difficulties for the forecaster to figure out what is telling the right story and what may be a little off. You've seen Doppler radar, being able to see the little blips of precipitation. If there's still some of that going on when you view this Friday morning, as I make this on Thursday afternoon, we've gotten a few rain showers and even a little bit of very small hail at the university today. Satellite images, forecast charts, our atmospheric soundings, those weather balloons are critical cogs of information to be able to keep the wheels spinning on our forecast models. And then even just to be able to look up in the atmosphere and see how the wind is behaving with height, these profiles of verticality with wind. And so when we do the forecast, we're basically first trying to take a moment and see what has happened. Without some knowledge of the past, we aren't going to have a really good handle on the present or on the future. So for instance, on a day like Thursday, again, more than likely a day or two before you're doing this, it's chilly, there's rain showers, but what's happened? I've gotten an idea of the features that have been going on in our weather over the past day, and as we kind of transition back into this trophy pattern from what was a pretty warm Wednesday, and that's still going to be part of the rule as we go into the day on Friday. But as we'll show in some of the upcoming models, next week looks awfully nice for October. What's happening right now? Well, we got a trough, we got some winds coming off the lake, it's breezy because we got a pressure gradient, it's cool because we're starting to lose sun angle, and we got clouds in the atmosphere, and our upper level thicknesses are low, so there's a number of factors going into the fact that it's kind of chilly outside on Thursday, and it's going to remain chilly through much of the weekend. And so understanding what we know about the atmosphere is a critical cog to understanding what will happen. And obviously all the time, to be able to gain forecast credibility, meteorologists are trying to understand the why. And so a little bit going back in history, years and years ago, before the advent of computers, most everything that we were dealing with was plotted by hand. You've had the chance, or you're having the chance, at least in your assignment number 2, to be able to draw some frontal boundaries, analyze air masses, isoplus some sea level pressure values. But a lot goes into actually making these maps. Students here at Valpo that go through the meteorology curriculum make a large number of maps. This isn't something that has simply disappeared with the advent of computers, because it allows you as a forecaster to gain a more intimate understanding of what's going on in the atmosphere. But many years ago, you didn't have a whole heck of a lot because we didn't have computers that were able to churn through these relatively difficult equations on very large spatial scales, and so we had those observations, and well, we kind of used those as best as we could to be able to give an idea of what would happen in the future. One thing we can bring up at some point is the first ever tornado warning that occurred at Tinker Air Force Base. A couple of folks in the Air Force, Fawbush and Miller, basically realized, hey, we had a tornado to hit the base a week ago, and today the conditions are like that day, so we're going to put out a tornado warning. This wasn't a tornado warning in the sense of what we're used to. Hey, there's a storm right in your right on your front porch and it's about to hit you, so take cover. No, this was in the morning, and it just so happened that that afternoon a tornado hit Tinker Air Force Base. Unbelievably fortuitous, but still, the idea that using those past and current observations were really all we had to rely on in order to make a forecast. And so the best forecasts, even decent forecasts, were at best out to 24 hours. Models began in the 1950s. They've matured significantly in the decades. And again, we continue to test new models, much, much higher resolution, being able to drill down to neighborhoods as opposed to states that we would have been able to go to. Simply the computing power. If you're familiar at all with how we've improved computing power and how the doubling factors occur with computing processing capabilities, we've simply continued to advance this rapidly. And so, as I already alluded to, the fact is we're simply solving a series of equations of motion, continuity, things such as that are allowing us to get an idea of what the atmosphere is going to do based upon our information from things such as satellites and radiosondes. And so we get an analysis chart, which gives us an idea of what's going on right now, and realizing that just to make a 24-hour forecast for one hemisphere is millions of calculations. And this is why it's taken a long time for us to improve our capacity to forecast the weather. And so, yes, we can go back in time and realize there were days that these computers took up entire rooms. And so understanding 3-layer baroclinic model means next to nothing to you, other than the fact that now our layers are well into the double digits. 300-kilometer grid spacing. That would be effectively the idea of having a grid point in Valpo, and then maybe a grid point in St. Louis, and then another grid point in Cleveland. Whereas now we may have some models that are able to put out multiple grid points in the city of Valpo alone. And so they started off many years ago. IBM was still one of the big players in computers. And, well, not that you need to understand what a kiloflop is, but suffice it to say that whatever you're using with the phone that's probably within arm's reach of you as you watch this video has just massively more power than this entire computer that took over rooms. And so the models that exist today, essential to weather forecasting, there's a number of them that are put on NWP, standing for Numerical Weather Prediction. These are some of the ones utilized heavily in the United States. You have the Rapid Refresh model, one that is, well, what it says. It rapidly refreshes. It comes out every hour, and it goes out for 18 hours. The idea being that if you put out a model more frequently, it has to conclude pretty quickly. Otherwise, you're going to still be running the model when the next model starts, and that's not really good. So these models that go out or that are produced every hour can only go out for so much time. 18 hours is pretty useful, though, if we're looking at things like, is it going to rain this afternoon? Or what's the low temperature going to be tonight? The North American model, or the NAM as we affectionately refer to it, goes out for 3.5 days. The NAM is going to look again primarily at North America, but a number of these models encompass different parts of both the CONUS, North America, much of the Northern Hemisphere, and many of them are global, such as the Global Forecast System. 384 hours. And so what happens with models such as the GFS is to be able to run through this much time, the resolution or that grid spacing starts to increase as you go longer and longer on the period. And in fairness, our capability to understand the weather or accurately predict it 384 hours in advance is, well, okay. So let's take a look at a few models. In fact, I've already got these pulled up here. Going to Pivotal Weather, that first website here, you can see here I've pulled up some 300 millibar heights. So again, you got the solid black line showing your height in decameters. So like this, for instance, would be 9,600 meters above the surface. And this is the model from the morning on Thursday. This doesn't come out as frequently as other models. These come out every 6 hours. And so you can still see this feature here, this deep trough that exists over the eastern United States, and some ridging out to the west. And so we can run through this. In fact, I'll just use the scroll bar. You can see that trough is going to stay over the area here into the day on Friday. Stay troughing over the weekend. Going to be a relatively cool weekend, but you can see that ridge building out to the west. And that's going to start moving into our area by the early next week. So by Monday morning, more ridging. And you can see that jet stream that comes in strong, but at this point is trying to stay a little bit off to our north. And so what the jet stream is ultimately going to end up doing is keeping some of those colder temperatures. Again, remembering that that thickness or these heights are relative to temperature. And so there's a sharp contrast where you have this jet stream. It's a similar process that's happening with winds at the surface. So where we get this tight packing of the isoheights, we get these winds that may be 134, 140, 145 knots being forecast. And so as we run it forward, not that we have a lot of faith in it, continues to show that the jets should stay up to the north in Canada. Here's a trough coming on the west coast here at 240 hours. Looks like a pretty deep trough. Again, one of the jokes that meteorologists will talk about is if you want interesting weather, look along into the GFS. Something is going to be out there. And so, yeah, I wouldn't hold a lot of stock in the weather here for the middle of October. Again, this is looking out on a Friday, the 16th of October. A deep trough located right over Valpo. So we'll take a look at that in a couple of weeks and see how close to reality it was. If we look at some other models, this is from the NCEP, or National Center for Environmental Prediction. And so here we can just look at the precipitation and watch how we can simply have models that show precipitation accumulating. So you can see the little blips, especially on the southeast side of Lake Michigan, with some of the lake effect rains and showers and thunderstorms occurring. Another little wave coming through, but generally pretty dry period here. Now I'm looking now at the NAM model. And so here down at the bottom, we can see that this is the NAM accumulating all the precip over time. So this is looking for about a 3.5 day precipitation. So lots of areas such as Texas and the Rockies expected to stay relatively dry. We'll come back to this here in a moment or two. But let's go ahead and go back to our screen here. Shocking news. Weather forecasts are not always accurate. That is one thing that you have realized for a great portion of your lives. You expect it to be sunny when you go to the beach and it rains. You expect it to be cold and you put on a sweatshirt and it gets warmer than expected. And it's easy to point out when forecasts do go awry, and they still do. It is, to be fair, one of the few things that is dealt with in a predictive sense that has shown some strong ability relative to, say, things such as analyzing what are the expectations of the stock market or political things, or even to the point of trying to predict when an earthquake might occur. But we still have to make some assumptions. We don't have data in every single spot. We launch a weather balloon in central Illinois, we launch one near Cincinnati, Ohio, but we don't have any routine balloon launches, for instance, in the state of Indiana. And so we don't have all the data that we need to be able to make these predictions perfect. The models many times are not global, and this is due to limited processing speed. We still don't have unlimited processing speed, and so we're not able to make everything quote-unquote perfect. Many regions have few observations. We get a lot of these ASOS, or these Automated Surface Observation System forecasts out in the eastern United States, but a lot less in the west. And there's even areas that don't have Doppler radar coverage, especially in some of the higher terrain. Tough to get some of the small scale features. If you're from anywhere around Chicagoland, for instance, you know that there are days where the weather in Valpo is nothing like what it is in Chicago. And that's nothing like what it is in Southwest Michigan, especially as we start to get into winter and lake effect snow is possible. And so basically the fact is we can't model everything. And when we can't model everything, errors are bound to occur. These errors magnify over time. If you've ever heard of chaos theory, something with a butterfly flapping its wings in the Amazon rainforest, and what ramifications does that have down the road, chaos theory is actually a really big deal in meteorology. Small errors early on will amplify over time. And so one of the things we oftentimes look at is what's known as a spaghetti model. We try to see if we make small changes, small perturbations as we refer to them to a forecast. Maybe change it by a 0.5 degree, change it by 2 degrees cooler, a degree warmer. What ultimately happens over time? This is critical, for instance, when we do predictions of where hurricanes are expected to track. We make small changes to account for possible errors, and over time see how those errors amplify and what the possibility of outcomes might be. And so, for instance, this is a very old map, 2013, I guess that's not that old, looking at certain 500 millibar height levels. You can see in the cyan type color, 5,460 meters, in the red color, 5,640 meters, and then we kind of see control groups in both of them. So in this example, again, big ridge out to the west, a little bit of an interesting feature out here in Europe, but you can see areas in which, for instance, here off the Pacific coast, all the cyan and red lines are pretty packed together. We might have high confidence because it means even small errors aren't necessarily resulting in a big error. But look over the Great Lakes, especially at this 5,460 meter line. It's kind of all over the place. And this is only 3 days out, a 72-hour forecast. And so things like this are, well, less confident. We're not really as in tune with saying it's going to be a certain value, for instance, for a high temperature over the Great Lakes when these lines are all over the place. But what happens if we go out further in time? We get a plate of spaghetti. That's why these are referred to as spaghetti plots. This is a 360-hour forecast, so let me do a little math in the back of my head. 240 is 10 days, 15-day forecast. And, well, you tell me if there's a trough over our area or a ridge. We can't say. And this means that this chaos theory, these small changes mean massive, massive changes as we allow the errors to amplify and evolve over a long period of time. And so we'll conclude this lecture by simply looking at one more animation. And so what we're looking at here, again, this is off the NCEP webpage. This would be government webpage, NOAA. And so what we have here is we have certain height contours, again, around 500 millibars. And what I'll do is I'll move forward. So this is looking at what's going on right now. We just showed maybe about 5 minutes ago the trough over the eastern United States and the ridge over the west. And so if we start to move forward, you'll notice that if we go a day out, trough and ridge are still pretty much there. Still pretty much there as we look out 2 days. Starting to see a little more discomfort out here, but still, I mean, you're not going to think that all of a sudden this is going to change rapidly. If we move out further, even now, 84 hours, pretty good. 90, 108, 120, 144. Okay, we still have relatively high confidence of troughing across the eastern United States, but starting to feel a little less comfortable in how high or low of amplitude it might be. Keep going out, and all of a sudden you can start to see here by the time we get out to about 174, 180 hours, what's going on out in the Pacific is not going to instill a high level of confidence in a forecaster. And so this slowly devolves into a plate of spaghetti. In fact, if you start to pick out some of these lines, you can see, for instance, out here, we might have more of a troughing feature if we were to think that this model was correct, and a ridge factor, a ridge if we think this model would be correct. So we have really low confidence. Sure, we can see that the spaghetti is kind of concentrated in certain areas, but really all over the place. And if we move it all the way out to the end, well, now you understand why we don't have a lot of faith in long-range forecasts. And so if for some reason someone tells you, hey, 30 days from now the weather's going to be X, or if you really want to believe the Farmer's Almanac, I've given you good reason as to why that's not necessarily the best plan. What we do know when we're trying to make longer-term predictions is that things such as teleconnections, the idea, for instance, that features associated with an El Nino can have general pattern influences across areas such as the United States. That's where we can actually show some skill in making long-range predictions. All right, so this one a shade under 20 minutes, but it is the only video you have for this weekend. Have yourselves a great weekend, and we will see you in class on Monday. Take care, stay warm, and stay healthy.